Hey everyone. So today we are going to work through uh, three of the most important tools applied in the hydrology. So here's the big picture. Whenever rain falls on a watershed, three questions dominate engineering design. So first one is like how much runoff will there be at peak? That's problem one. So we will be using rational method for computation of that. And second one is what does the entire run of hydrograph look like over time? That's our problem two. We'll be using unit hydrograph for solving that. And third question is how long does it take water to travel from farthest point to the outlet? That's problem three. That is time of concentration. So let's start with the simplest and most widely used method in urban stormwater design. So for problem one, so here's the scenario. We have the 12 acres of site in Pennsylvania, currently flat, undeveloped, pasture with a 0 to 2% slope. It's about to become a shopping mall. Our job is to compare the peak runoff before and after development for a 25-year storm. So the tool we will be using is rational method. So let me write equation. So this Q is equal to C times I times A. So C is our runoff coefficient. So it doesn't have any unit. And I rainfall intensity. So here we will be using it as inch per hour. Whereas for area, like A denotes drainage area in acre. Whereas Q is like discharge in CFS unit. So, so here's an important thing to remember. When you use inches per hour for intensity and acres for area, the results comes out directly in cubic feet per second. That's not a coincidence. It's because 1 acre inch per hour is very close to 1 CFS. The conversion factor is 1.008, which we round to 1. So let's write input parameters for two cases like pre-develop and post-develop. So our main input parameters are area is 12 acres and our return period is 25 year. And for this uh, undeveloped flat pasture that is 0.0 to 2% slope, we will have like C is runoff coefficient will be equal to 0.34. It's from the table 15.1.1. So and its time of concentration is 42 minutes, and post developed it is post development time of concentration is 28 minutes. Land use is 30% roof, 40% parking lots, 20% grass, 10% grass. So we will be using all these land use and make a combined weight like here in the case of pre-development it is single land use, so we use directly C is equal to 0.34. So for post-development we have like four different land use, so we need to combine them and create a single combined weight. And so we will be using our rational method, which I already explained. So we need to get 25-year intensities for 42 minutes and 28 minutes. So here what we can do is we can go to, I will show you how we can go in this site. So first of all, let us type this NOAA Atlas 14 intensity measure. So it gives us like this NOAA Atlas 14. So when we go here, we can select state. We can select state from here as well as from here as well, like by clicking on the map itself. And our major aim is to compute like intensity. So here we can change from by dragging. Like it will be like we can select precipitation intensity, and since the area is given as Pittsburgh, we can type Pittsburgh. So Pittsburgh, Pittsburgh. So I type the Pittsburgh, PA, and we can see here as like cross. So this cross section denotes the Pittsburgh area, and when we go down, we will have the tabular format and graphical format. So based on this, like PDS, base intensity, duration, frequency, IDF curves. So this latitude and longitude refers to our area location, that is Pittsburgh. So here this legend shows average recurrence interval years. So we will be using this, which I have already pasted here. So since like we don't have 42 and 28 minute here, so we need to do some interpolation and do some average things. So for from the table, you can do from either way, like using this graph as well or this table. So for the post development, so our rainfall intensity at 28 minute will be around 3.2 inch per hour. So it's like 28-minute falls lies in between this 15-minute and 30 minutes. So when we do some interpolation, it will be like 3.2 inch per hour. It's approximate. You can have more like another value as well. And for the pre-development, so our precipitation intensity at 42 minutes, that is like it lies in between 30 minute and 60 minute. And when we do some interpolation, so it lies between 3.17 to 2.06. So I just approximate it as 2.7 inch per hour. Since like for the first case, we have C, we have I, we have A. So for the pre-development runoff, so our Q will be equal to 11.02 CFS. And since for the post development, it has four different land widths, we need to calculate combined C factor. So that's it. So land use for roof is 0.3, 30%, and this is the factor runoff coefficient for the roof. And for the parking lots, we'll be using 0.88, since it can be concrete as well or asphaltic, so we can use 0.88 or 0.86. And for the grass areas, we'll be using the C as 0.4. And for the street, we'll be using asphaltic, so I choose here 0.86. So when we do combine here, so we will be getting 0.781. So after that, like Q post will be equal to 0.78 times 3.2 times 12. So see, this is from I, and this is we just got combined C, and this is area. That's it. So you can also notice one thing that is important already. So here development didn't just change the runoff coefficient, it also shortened the travel time, which increases the design intensity. It's a double hit. So hence our maximum pre-development runoff is 11.02 CFS, and maximum post-development runoff is equal to 29.99 CFS. So you can have different values based upon this runoff intensity, and then this C. So development of shopping mall will result in like increase of approximately 19 CFS in peak runoff. So now let's go to question number 2. So the question asks about finding the unit hydrograph for 1 hour storm, and then like a 3 hour storm that gives 2 inches of rain. And second part asks us about to compute storm that gives 2 inches of rain in the first hour, and then 3 inches of rain over next 2 hours. And the basin area is 2000 acres, and base flow of river is 150 CFS. So it is the one of the important things you need to learn, because it will be used in flood modeling as well, behind scene when you use HEGRAS or some other hydrological modeling things. Behind the scene, this unit hydrograph is working there. So let me explain what is unit hydrograph. So unit hydrograph is the direct runoff hydrograph resulting from 1 inch of excess rainfall distributed over uniformly over the basin for a specified storm duration. It's a fingerprint of the watershed. So once we have it, we can predict a runoff from any storm of that duration. So here, first we will be computing 1 hour unit hydrograph, and then we will be predicting for 2 inches of rainfall for 3 hour, and this second part as well. So for solving this problem, so we can follow certain steps. First one is like we need to separate base flow. The measured flows include base flow and water that was already in the stream from the groundwater. We have to subtract it out. So here we can see like a direct runoff hydrograph will be like this total runoff minus base flow. Since our base flow is 150, so 150 minus 150, so it will be 0 for time 0. And second step will be like computing the total direct runoff. We need the total volume of direct runoff. We sum the direct runoff hydrograph ordinates and multiply by the time step in second. So here like V will be equal to DRH ordinate times 3600. So after like this runoff, and then we have base flow separate, and we will compute like a direct runoff hydrograph. So that's how we get this, and I will show you later how we compute that. And third step is determining the depth of excess rainfall. To convert volume to depth, we divide by the basin area here, and then at last, we will be deriving the 1 hour unit hydrograph. That is. So let's go like first of all, like let's find the rainfall depth. So our volume will be DRS times time interval. So DRS will be 3457 times 360. So I will show you how I got this. So DRS will be like just runoff minus base flow. So this 0, and then we just subtract runoff minus base flow, and when we uh, sum of all these DRH, we get this 3457 times 3600. So it will be like around 1200, 12445200 feet square. And our area, since it's an acre, so we need to convert that into feet. We convert that into feet, and after that we have volume and area. We will be computing depth. So depth will be equal to B by A. So our depth will be 0.143 feet. So when we convert that into inches, it will be 1.714 inches. So that's our excess rainfall. And for deriving the 1 hour unit hydrograph, so unit hydrograph will be equal to DRS divided by 1.74. So since we have like time runoff base flow, we obtain DRS by subtracting runoff minus base flow. And when we divide this DRS by this axis rainfall, that is 1.714, we get 1 hour unit hydrograph. So it's just dividing by here 1.74 dividing by 1.74714. So it is the same process for all things here. And when we plot the 1 hour unit hydrograph with respect to time, so figure looks like this. So here we can see like in the period of 2 to 6 hours, the unit hydrograph is peak around 330, yeah, maybe around 330. And for part A, 3 hour uniform storm 2 inches total. Now we use the above unit hydrograph. Part A gives us 3 hour storm with 2 inches total. If we assume it's uniform, that's 0.667 inches uh, per hour for consecutive 3 consecutive hours. To build the storm hydrograph, we use convolution. Think of it as applying the unit hydrograph once for each hour of rain shifted in time, then adding them up. So here, our convolution will be equal to Qt P1 times US plus P2 times US T minus 1 plus P3 times US T minus 2 plus 150. So each rainfall pulse multiplies the entire US and gets lagged by 1 hour. P1, P2, P3 are all 0.667. So hour 1 rain activates the UH starting at T is equal to 0, and hour 2 rain activates the same UH but shifted 1 hour later, and hour 3 rain activate it shifted 2 hours later. And when we sum the three contribution, add 150 CFS and get the complete storm hydrograph with our rainfall pulse M is equal to 3 and L is equal to 13 US ordinates. Uh, the result has N is equal to L plus M minus 1, so it will be equal to 15 time steps. So we need to have 15, and now when we plot, we already have this time steps. So here previously it was like around 12, but since here we have like 15, so 15 time steps, so we need to have at least 15. And rain one, it's 0, it's same thing, we don't need to do anything. So here we already have like a unit hydrograph. So here we have 23.9 in time step 1. So we will multiply that with this 0.667. So we got that. And same thing here. So it's like in the rainfall 2, we will be shifting 1 hour and then like multiplying that 23 point something times 0.67, and we'll be getting like 15.9. And similarly for rain 3, that is 0.667, we'll be like lagging by time like 2 hour, and then we'll be getting 15.9 again. And when we sum at 0, so it will be our total hydrograph will be 0. But since we have 150 as baseline base flow, so our total hydrograph will be 150. And similarly for time 1, so it will be like 15 plus 150, so it's 165.9. Similarly, we add all these things and we'll be getting total hydrograph as 263, and same thing for all of them. And when we plot that, so the peak total direct runoff is at around this 650 CFS at hour 5, giving a total hydrograph peak of about this 816. Notice how the peak is broader and delayed compared to the original unit hydrograph. That's the smoothing effect of distributing rain over 3 hours. And for part 2, part B, non-uniform storm, that is 2 inches in hour 1, and for next 2 hours it will be like 3 inches, and we can divide that in by 2 to get like a 1.5 for second hour and 1.5 for third hour. So it is more realistic. However, rain upfront, like 2 inches in the first hour, then 3 inches is split over the next 2 hours, and same convolution process, different multipliers. That is P1 is equal to 2, P2 is equal to 1.5, and P3 is equal to 1.5. So here also we will be using the previous formula, that is convolution formula, which is like Qt is equal to 2 times UST plus 1.5 UST minus 1 plus 1.5 times UST minus 2 plus 150. Because the rainfall intensities are much higher, total of 5 inches versus 2 inches. The resulting hydrograph is will be like dramatically high. So here we'll be doing the same thing, rain 1, and we'll be lagging the unit hydrograph by 1 step and multiplying by 2 for rain 1, and it's like same process. And this is what we got. And this is the figure when we plot this total runoff hydrograph, rainfall hydrograph versus time. And here from this figure, we can see the peak DRH is about 1668, this one. That give us cumulative like total hydrograph of 1818. Compare that to 816 in part A, 2.5 times larger from a storm with 2.5 times more rain. That's the beauty of superposition. The unit hydrograph scales linearly. And now let's go to question number 3. Before I jump into question number 3, so let me discuss what is time of concentration. So the time of concentration is the time it takes for water to travel from hydrologically most distant point in the watershed to the outlet. It's critical because it determines which rainfall intensity to use in rational method or other methods. So in this, in our problem, so water travel through 3 different reaches, each with a different flow mechanics. We calculate the travel time for each reach and add them up. And our first reach is 150 feet, which is about seed flow in dense grass at 3% slope. Seed flow is that thin, shallow film of water moving over the ground surface before it organizes into channels. It's the slowest type of flow and typically limited to about 300 feet. So for solving this, we will be using the this Kirpich equation for overland flow travel time. So that will be like TC will be equal to 0.019 times L. L is length of watershed and S is slope. So we have length as well, we have S as well. And so since so we convert that 150 feet into meter, and then we get like the time of concentration for reach AB seed flow is about 1.4 minute. So what we can do is we can use time of concentration for computation of time of concentration for overland flow. We can use this kinematic wave equation as well. So since here we do not have this IE, we can assume like as some return period and use the same like Noah's intensity depth intensity precipitation intensity from the Noah's like we did in first. But since we have another alternative, this Kirpich equation, so I'm following that here. And these are all the equation. And for ridge B, it is shallow concentrated, 1200 feet, unpaved, and has 3% slope. So once the water concentrate into small rills and soils, it moves faster. And for shallow concentrated flow, we can use TR55 concept like which is given as this figure 3.1. So we can use like here is like unpaved for computing average velocity. We can use this unpaved and like this is water course slope feet. So the our slope is 3%, so it will be 0.03 here. And when we like just connect it here, so it will be like unpaved. And when we go down, it will be around 2.4. And for computation of time of concentration, so it will be like length divided by velocity. So it's for when we need in hour, and so we don't need the time of concentration in hours, so we will be using just L by B. So our L is equal to 1200 feet and our B is equal to 2.4, so it will be around 500 second. And so when we convert that into minute, it will give us 8.3 minutes. And if you want to know more about this, you can go to this PDF in the from the internet as well. And for the question number two, no, question number three, reach CD, that is channel flow. So we will be using their overlap for reach CD, channel flow 2100 feet, natural channel 3% slope. The final reach is the natural channel. We are given the cross sectional area as 9 square feet and weighted perimeter as 7 feet and slope remains 3%. We need Manning's equation for open channel flow, that is this one. And the first the hydraulic radius R will be equal to A by P. So we are given area as well, and we know about our P as well. And when we convert that into feet to meter, so we get like for area 0.84, and for P we get like 2.1336 meter, and we will have this hydraulic radius. And so we will be using this many equations. So velocity for channel will be given as this will be km. So this is our n 0.05 Manning's equations. So this is from hydraulic radius divided by perimeter, and this is slope. So we get our velocity as 1.86 meter per second. Uh, and when we compute time of concentration, so our length is equal to 640. When we convert that feet, I convert that into meter from feet, and so we will have like 343.9 second, and when we convert that into minute, so it will be 5.74. So before I wrap up things, so let's connect the some of the dots. So let's step back and see the big picture. We have covered three tools today, and they are not independent. They form a connected workflow. Time of concentration, it tells us how long the watershed takes to respond. This drives which rainfall intensity to use. And problem one, that is rational method, it it uses that intensity to calculate the peak discharge, simple, fast, and perfect for a small urban catchment. And problem second, unit hydrograph, it gives us full time varying response, critical for designing detention pond, basin, sizing culverts, and understanding how different storms of different pattern produce different floods. So some of the key takeaways from this video or this recitation class are this development will dramatically increase runoff both through higher sea and shorter time of concentration. It's the compounding effect. And second one is unit hydrograph leverages superposition. Once you have the unit hydrograph for 1 inch, you can predict the response to any storm using convolution. And another one is time of concentration is the sum of individual reach Travel times is calculated directly depending on the flow regime.